topic. So I would like to give. I want you to give me some keywords that what you have actually learned for chapter 3. Okay. Okay, chapter 3. Any keywords that you recalling breakfasts? Alright, it's very good. So, come across of these breakfasts, right? Very good. What else? Breakfasts. Okay. Breakfasts. Alright, so what else? This is informed search. How about? Okay, very good. Yeah, you learn about uninformed search, which is the topic. Uninformed search. Alright, so what else? New. No game. Okay, time efficiency, I would say is performance comparison, performance. Under performance. So you have a four performance here, time efficiency or time consumptions. Yes, is that okay? Optimality, very good. Okay. Optimality. I don't want to disturb you, makan. Cool. Completeness. Alright, completeness. One more. Space. Okay, very good. Space. Okay, space efficiency. And you have also learned about like limited depth search, okay, iterative deepening depth search, and bidirectional search. But as I mentioned last week, you should focus more on the breadth search and depth search. So the limited depth search, iterative, and bidirectional search are just variations from these two search. Actually, improved versions. Alright, so and then after we perform the search, we would like to compare the performance in terms of the completeness, optimality, space, and also the time. So this is a chapter 3, but before this, we have learned on the problems and goal formulations, right? So you learn about this, define the problem, define the goals properly, and choose the strategy. So we have a two type of strategy here. One is informed search, another one is uninformed search, another one is informed search. Okay, so what is the difference between uninformed search and informed search? Is where uninformed search is solely depends on the patterns. Right, so breadth search follow this horizontal. If no solutions, you go to the next level. Right. So depth search, you go to the one directions. If no solutions, you backtracking. Okay, go to other branch. So this is the patterns. Although we know that this so-called this part is not going to lead you to solution, but we have to search also. The agents will just provide the agent will still search the path because the agent doesn't know that there is a solution here. So you just search based on the patterns. Meanwhile, informed search is not based on the pattern, but it's based on the heuristic cost or maybe some information, right? So it actually depends on heuristic cost. So I'm going to show you what is heuristic cost later and how to generate heuristic cost. Okay, and how the agents perform the search according to the heuristic function that defined by the user or us, right? Okay, so at the end of this class, you should be able to define and evaluate what is heuristic search, or sometimes it's known as informed search, right? Informed search or heuristic search. So and also we have how many techniques? We have 4 techniques here, right? For the heuristic, we have 4 techniques. Okay, so I'll bring it out here. So you have hue crime. Okay, you have best first. and you have A star. So these three are the most common techniques under informed search. So meanwhile, hue crime, you can actually branch out another two. It's known as simple hue crime or steepest access hue crime. So meaning that we are going to learn four algorithms today. So each algorithm has its own limitations and advantage. So probably you confused during the class, but maybe afterwards we want to make a summary so you know which one is the best and which one what is the limitations and the advantages, alright, for each of these algorithms. Okay, so this is what we covered last week on informed search. So this week we are going to cover the informed search to make this chapter, the whole chapter, complete. So we have covered chapter 2, chapter 3, and chapter 4. So next week we are going to go into another applications. Alright. So before we start this heuristic search, okay, so you have to understand first what does it mean by heuristic functions. Okay, so this is the first keywords that you have to understand first, right? You have to be clear what is heuristic functions, because this heuristic functions is going to generate the cost for these algorithms. If you don't know, if you don't understand what is heuristic function, you probably lost in all these algorithms here. Okay, so what is heuristic functions? This is the definitions. It's a function that rank alternatives at each branches based on available information to decide which branch to follow. So meaning that heuristic functions is actually a function will generate the heuristic cost. Okay. Alright, heuristic cost is actually a value, right? It's actually a value. Alright, so that the agent knows where to go. So I'll repeat again, what is heuristic function? It's actually a function that eventually will generate the cost. It's a value. So that the agents will just move the path, okay, decide where to go. So I move to the left, so I move to the right. It solely depends on the cost. Right, for example, you have a path is stated like A, it's node A. So you can travel to node B, you can travel to node C. So B, let's say you can go to D, E, F. Okay, C, you can go to F as well. Let's say. Okay, so your starting point is A, you want to travel to F. So you have some distance. Let's say is 3, 2, 1, 4, 5. So this is 1, this is 3. Okay, so you have a distance of let's say I will assume that this is a cost. Don't worry about this value and how to generate the value here. So it's actually generated from the functions. So assuming that the heuristic cost from A to B is 3, 2, 1, 4, 5, 1, 3. So what does it mean by this definition? A function that rank alternative. It means that we start from the A, okay, and this cost here will tell the agents which path to go. Alright, so this is shorter, right? So we will travel this path because we would like to travel in the shortest distance. Alright, assuming that the function is to arise in the shortest path or shortest distance, so this value is going to give a hint to the agents. Okay, so this is lesser than this, so we should go to this path. Okay, so we add a C here, so we should go to F or I. So this is shorter than 3, so we have to go to this path. Okay, so that's the idea. So where we are going to rank the alternative means that we have a lot of alternative here, we have a lot of successors. So this cost will so-called allow the agent to decide which path to go. So take the minimal one. Okay, so if contrast to this uninformed search where it depends on the patterns, we can actually skip this path already, right? We skip this path, we will straight away travel from here to here and from here to here. Then we set the time and memory to travel this branch. Okay, so there's a big difference. I repeat again. So uninformed is based on the patterns. We have to travel from here to here, to here to here, here to here. Although we know that this part is not going to give us a solution, we have to travel also. But by using the heuristic cost, the agents will know that this path is is actually useless. It's not going to give you solutions. So we travel this path based on the cost. So don't worry about the cost, don't worry about the function first. Alright, so that is the idea. So the cost will tell the agents where to go. Alright. So but however, to design the heuristic function is very difficult, it's very challenging. It solely depends on the experience or the intuitions. But don't worry about that. You're not going to learn how to design the heuristic functions in this course. You are just apply. So most of the time we will just give you the heuristic functions, and you just need to apply the heuristic function to generate the cost. That's it. You don't really need to learn how to design the functions. Okay, unless you're doing or pursuing master or PhD, yes, then you have to design your own heuristic functions because you want to develop a system that probably can reach to the destination in shorter distance, right? Then you have to design your own functions. But at this moment, no need. You just apply. Alright, so heuristic is only an informed guess to the next step to be taken. Right, so tell the agents where is the next step. But however, a poor heuristic functions can probably lead to the suboptimal solutions or fail. It means that if you have designed the heuristic function is like not appropriately, then your solutions may lead to fail or not lead to solutions but not the optimal one. Alright, so that is the limitations using the heuristic functions. So assume that, so this is one of the examples. So the heuristic function here is to design a functions where we will calculate the number of tiles at the correct positions. Right, so that is the heuristic function. Is to calculate the number of tiles at the, this is not the right place, it's not the right, left, up. This is actually referred to correct place. So how to calculate the correct place? It's very simple. You just need to look at this final one. So you have 1, 2, 3, 8, 4, 7, 6, 5, right? So we just need to compare the current state with the goal state. So check the first tile. The first tile is 2, but the first tile here is 1, so it's wrong. It's wrong, then we don't give any value to the first to the wrong tiles. Okay, 8. So at the second tile is 8, but here at the second tile is number 2. So it's wrong again, so we don't give any value to 8. So we look at the third one. The third tile is number 3. So the third tile is number 3. It's correct positions. If correct positions, we give 1 mark to this tile. So we have one point here. So check this one. So this is wrong. 6 also wrong. 4 correct. So we add 1 mark. 7 is correct, add 1 mark. 5 is correct, add 1 mark. So you just total up 1, 2, 3, 4. So there are 4 correct tiles from the current state to the goal state. So the heuristic function, the heuristic cost is equal to 4. So by using this function, which is to calculate the number of tiles at the correct positions, it generates the heuristic cost, which is 4. Okay, is that clear at this moment? Okay, we have a functions. That functions is going to generate the cost. And this cost, what's the purpose? Agents decide which path to go. Alright, so let's move on to the first algorithms. Alright, so I believe you should know what is heuristic function now, what is the purpose, and what will be generated from the heuristic function. It will generate the cost. Okay, so let's move on to the first algorithm. So it's known as the hill climb. So we have 2 algorithms here. It's known as simple hill climb and steepest access hill climb. So it's about the same. It's about the same, but the algorithm will be is a small difference here. Okay, the hill climb here, the limitation of hill climb is where is less combinationally explosive as locally. Alright, it means that actually this hill climb is not really efficient because this hill climb is not allowed to backtrack. Okay, not allowed. So due to this reason, it makes the hill climb is not effective and may trap inside so-called lead you to the failed solutions. It's not complete. Alright, it's due to the not allowed to backtrack. So I'm going to show you the example now. So this is the first algorithm. It's known as simple hill climb. Alright, simple hill climb is where we start from the initial state. Okay, we start with the initial state. So we go into the for loop. Select an operator. So look at this. This is very important. Select an operator means that we just choose one operator here, mean one successor function, only one actions. So let's say A, you can move to B. Okay. So we don't look at the other first because the algorithm stated select an operator. We just go to the first successor function here. So A can travel to B. So let's say I have some functions here, okay, heuristic function. Okay. So this heuristic function generate a cost which is, let's say, 4. Okay, don't worry about what is heuristic function at this moment. It will generate a cost which is 4. So let's say the goal for your this case is equal to 8. Okay, your goal having a heuristic cost which is 8. So meaning that you have 4, you want to travel until 8. You want your destination is 8. Now at this moment it's only 4. So you travel to B, we use these functions to calculate, okay, you get 5. Okay, what happened here is, if the new state is better than the current state, then only we perform operator make new state to the current state. We have to ensure that this state, the heuristic cost here, must be better than this one, then only we can continue. Alright, if continue, we get C, let's say. So again, we generate the cost, let's say, is 5. So my questions, 5, is it better than 5? Is 5 better than 5? Alright. Anyone say yes? Alright. Right, 5 is just equal, it's not better than 5, right? So 5 is not better than 5, so what happened? Okay, so what happened is, you have to come back here and choose another operations. Alright, so this is, let's say you generate C, 5 is equal to 5. So means that we are not going to continue the operations here. We have to go back to B and check, do we have any other operations or not? If let's say yes, okay, we can go to D. Let's say H equal to 5 also. 5 again is equal to 5. It's not better than B, so we check, do we have other operations? Let's say yes. E. So we calculate the cost, let's say it's 6. Oh, this round, 6 is better than 5. We can continue. Let's say E, generate F. H, we calculate again, let's say 4. So 4, is it better than 6? No, right? It's worse than E. So we stop here. We find other operations under E. Yes. Let's say H. We calculate. Let's say H equal to 4. Or let's say H equal to 4 is worse than E. So we go to other operation. Let's say there's no more operation here. We stop here. So fail. This is the algorithm for simple hill climb. Alright, not allowed backtrack. So once we read here, there's no more solution, we cannot go back here. So that is the reason why I say hill climb is not efficient and not effective. Due to these reasons, it's not allowed to backtrack. Okay, so look at these examples here. I used back the same example just now. This is the goal. Alright, so that is the goal here. So this is the initial state using the successor function to calculate the correct tiles. Number of correct tiles, so we have 1, 2, 3, 4. 4 is still far away from 8. Right, 4 is still far away from 8. So what will happen is, so we follow these successor functions or the operators. So we have to move these empty tiles to up. If you move up, so this 6 one will go down. So if 6 will go down, we compare again. So we have 1, 2, 3, 4, 5. 5 correct tiles compared to the goal state, right? So we have 5 here. 5, is it better than 4? Yes. So what we'll do here is we will continue to move the tiles to up because we go to the next level. We have to reset our sequence. So move these empty tiles to up, so 8 will come down. So 8 will come down, what happens? So you will have a heuristic cost 1, 2, 3, 4, 5. 5, is it better than 5? No. So what happens? We go to the next operator, which is right. So we move these empty tiles to the right hand side. It will generate 4. 4 is worse than 5. So we don't continue. We go to the next one, which is move the empty tiles to the left hand side. We move this to the left hand side, it generates cost, which is 5. So 5, is it better than 5? No. Do we have any other movement here? No. You cannot move down because if you move down, it's actually back to original state. So what happens? There's no solutions in this case. Start here. Okay? Because why? Not allowed backtrack. examples. So now we have the goal state heuristic cost 8. This is current state 1, 2, 3, 4, 5, 6. 6 is quite near to 8, so we start to explore. So look at the successor functions. Up, you cannot move up. Left, yes, you can move left. So let's move left. If you move left, 1, 2, 3, 4, 5, 6, 7. 7 is very close to 8, so we can continue because this state is better than the balance node. So 7 continue. Can you move up? No. Left, cannot. Right, cannot, because if you move right, you back to original state. Alright, so you move down. So if you move this down, 8 will go up, right? So 8 go up, so it drop back to 6. So 7 is better than 6, right? 6 is worse than 7, in other words. So we cannot continue. So we move to other operations. So there's no more operator that you can move. Again, we start here. No solution in this case. Okay. For these algorithms, you have to answer the heuristic cost of the current state must be better than the balanced one. Then we only proceed. Else, you cannot continue. Okay? Else, you cannot continue. Okay, so this is steepest ascent hill climb. The way you expand is quite same, but instead of expand a single so-called nodes, we expand all. So this is simple hill climb. So this is steepest ascent hill climb. So assuming that you have an A here, so since our goal is 8. So let's say current state is 4. If you look at these algorithms, it stated generate all successor state. You generate all, just like breakfast. You generate all first. Let's say you have B, you have C, you have D. You generate all, you calculate the cost. Let's say this is 4, this is 5, this is 6. So which one is better than the parent node? C and D, CD, right? CD is better, so B is disqualified, right? Because it's equal. So C and D is so-called better than A. So which one to choose? D, right? Why? Select the successor state that yields the highest heuristic value. So it's not necessarily you obtain the highest. It depends on your heuristic function also. In this case, you have to select the highest because why? Because your target is number 8. So which one is closer to the goal? D. So we select the D. Okay, so we expand all again. Okay, so we expand all again. Let's say H equal to 5, H equal to 4, H equal to 4. Okay, we generate L, we assess. So which node is actually the heuristic cost is better than D? Okay, let's say D you have a H6, E5, F5, G4. Which one is better than D? None, right? If none, what happened? Stop. Fail. Why? It's not allowed backtrack. That is the nature of the hill climb. It's not allowed backtracking. That's why hill climb is not always a good search because it may lead you to failed solutions. Alright, is that clear? Okay. So look at these examples here. 8, you have a goal state, same, H equal to 8. So current state is 2. It's still very far from the goal. So we expand all the possible states where you can turn out left or right. So you have 3 nodes here. So compare. Which one is better than the current state? Obviously, only the first one. So we expand the first node. Expand. There are the 3 possible actions here where you can move left, right, and up. Right, up, left, and right. So you have another 3 successor. Find out their heuristic cost. So 3, 3, 3 again is equal to the parent node. Fail. I'm not allowed to return. Okay, so um, don't use hill climb for any whatever reason. Don't use hill climb because it's not going to give you the solutions. Right? It's a very bad technique. But then, because of the hill climb, the researchers start to improve. That's why we have the bachelors and also we have an A star later on. Okay, we cannot say, oh, this is failed. Why we still have this as our theory? Because of the failure here, then we have seen the improvement from the hill climb. Okay, we will see later on how the best versus works and A star works, right? So these two techniques allow backtrack. Okay, so steepest ascent hill climbs face dead end also. So all heuristic courses are the same. So this is probably known as practice. So right, in hill climb, there's one phenomenon is known as local maximum. Okay, so we have these situations known as local maximum here. So there are three situations. The first one is known as foothill. The second one is known as plateau. The third one is known as ridge. So what is foothill? Foothill is where, foothill is where you have node, let's say h equal to 4. Okay, you go to B. B you have 5 here. 5 you generate C. Let's say this one drop back to number 4. This is foothill. You can imagine that, let's say I represent inside a graph here. You have a value 4. This is a goal, let's say. Okay, 4. You climb the hill, you reach number 5. Okay, you reach number 5. So you go to the next level, back to 4. Okay, your goal is still far away. So this is foothill. Okay, foothill. Yeah, what is the Chinese in foothill? 山脚，山丘. It's just a small hill lah. You have a big picture here, you have a big goal here, but it's just a small hill. So this is called foothill, a small hill here. Okay, so what is plateau? So let's say you have A. We are using steepest ascent, let's say. So this is 4. So you have B, let's say C. So this is 5, this is 6. So we choose 6 because 6 is better than 4. We expand. So let's say you have B, E, F. So this is all also 6. This is practice. Why? Imagine that you have the value 4 here. You go up to 6. Alright, so the step in front of you, all number 6 also, is flat. So agent don't know where to go. So all flat. Right? This also 6, this also 6, this also 6. So practice. Okay. So the last phenomenon is known as ridge. What does it mean by this ridge here? If you imagine that the steepest hill climb, we expand all right. So let's say the value inside the circle is the heuristic cost. So we have a 2 here, expand, we have 4, 2, 3. So we know that 4 is better than 2. So we will ignore 2 and 3, right? Because we choose the best one. So let's say we choose number 4. Okay, you can travel. Okay, you reach the goal. But due to the nature of you choose the best one, you may miss out the path that will give you the optimal solution. Right? Like in this case, 3 is actually the path that gives you the optimal solution. But due to the nature of like the steepest hill climb, you choose the best one. You follow this path. Then you miss out the better one. Like what Chinese say lah, you don't because of 1 tree then you sacrifice the whole forest. The best one is always in front of you. Don't struggle with the garden. There's the best one at the top. Alright, so that is the 3 phenomena. Okay, and then always remember what is the limitation for hill climbs, not allowed backtracking. That's why it may lead you to fail. So this is not a good algorithm. Hill climb is not a good algorithm. So what is the difference between simple hill and steepest ascent? Simple hill is like a depth versus we go one direction. As long as there's back, then only we go to the next operator. bad, go to the next operator. So the steepest ascent, we like a breadth versus. We expand offers. Assess which one is the highest and better than the current state, we expand again. That's the only difference between steepest ascent hill climb and simple hill climb. New member? Never seen you before? Is there? Oh, so this week suddenly you come back. Alright. Okay, so I hope you have a better understanding now of the steepest ascent and simple hill climbs. Right, so you have a exercise in tutorial, I believe, the question number 1. Try that questions. So you have a steepest ascent and simple hill climb. Alright, so you will get more so-called understanding through the exercise. Alright, so this is just a theory. So what is the fit tube, breadth tubes, and also ridge. Okay, so alright, before we take a rest, so I would like to move on to a very small topics here. It's not very important, but I will just let you know that just now we mentioned about the heuristic function, right? So there are actually two types of functions. It's known as the local heuristic functions and global heuristic function. Right? It's not algorithms, but just the type of heuristic function. What is heuristic function? Again, used to generate heuristic cost, so that the agents can decide where to move. Okay, so we have two types of algorithms, or two types of functions, sorry. Okay, so which is a local heuristic functions and global heuristic functions. So local heuristic functions here is very simple, very easy to design, but probably very inefficient and ineffective. Meanwhile, global heuristic, we take the big pictures. The moment that we design the heuristic function, we have to look many factors. Okay, we have to consider this factor, then we design. So because of that, it's actually quite difficult to design the global heuristic functions, but probably it will more efficient, effective compared to the local heuristic. But nevertheless, yeah, both locals or global do not guarantee you to reach the optimal solutions. Okay, come back to the theory here. Heuristic function is designed based on the experience or the intuitions. Right? So you may design a wrong heuristic function. Right? So we have two types here. Look at this first heuristic functions known as local heuristic. Okay, so don't ask me why the block is rest on the right place. As one is designed by someone, right? So it decides that if let's say a block, we have a block here. Okay, so this, do you know this game or not? So you have a 3 block, so you have to shift the block, like put the C on the floor, and put the A on the floor, and then put the B. So you have to stack the floor, or stack the so-called the block, arrange the block so that you will reach this situation where A is on the B, B on the C, and C is on the floor. Right? Okay, so look at this heuristic function here. If the block is rest on the right place at 1, else -1. So it means that, let's say this is the goal state. Okay, we know that A must place on the B. This is local, right? We just look at the A. A, is it placed on the B? Correct. B, is it placed on the C? Yes. C, is it placed on the floor? So this is what we concern. We just want to look at this particular block. So let's say we have a current state. We have a C, A, B. So we just need to look at C. C placed on the A. Compared to the goal state, C is placed on the floor. So is it correct or wrong? Wrong or correct? Compared to the goal state. Wrong, right? Because goal state C placed on the floor or the table. But here C placed on the A is wrong. So according to the function, it says that if wrong, we give this value, -1. Now look at the A. Okay, A placed on the B, right? But here A placed on the B, correct or not? Correct. So what happens? It rests on the right place at 1. B on the floor. This one, B on the C, correct or wrong? Wrong. So -1. So you just add up this value together, -1, -1, +1. So you get -1. So this is known as local heuristic function. So where we just focus on this particular block, whether this C is it placed on the A. We don't care whether B is together with the A or not. We don't care. We just look at the C. Okay. So this is local heuristic functions. Let's see the efficiency here. Right, by using steepest ascent hill climb. So steepest ascent is we expand all. Right, expand all. So at this moment, CAB, what is the successor? I think there's only one move, which is move the C on the floor. If you move the C on the floor here, so you will get A, B, and C here. So we calculate the heuristic cost. A, is it on B? Yes, so we have positive 1 here. B, is it on floor? Wrong. If we compare to the goal state, so negative 1. C, is it on the floor? Compare this. Yes, C is on the floor. Yes, so positive 1, negative 1. Add up together, you will get positive 1. Alright. So, positive 1, is it better than negative 1? Yes. So, we expand all. So, there are two possible movements here. You can either put A on the floor, or you can also put A on the C. So, you have two possible movements. Again, calculate the heuristic cost. So, you have negative 1 here, you have negative 1. Both also worse than the parent state. Right, so we get stuck. Okay, so by using local heuristic functions, you can see it's not very efficient. You get stuck here. Alright, so let's compare it to the global heuristic functions. So this is global heuristic functions again. So this is designed by someone else. It stated that for each block that has the correct support structure, plus 1 for every block in the support structure. For each block that has incorrect support structure, you put negative. Negative 1 for each block in the existing structures. So it's very confusing. Okay, so we use back the situation here. Alright. So we have a CAB. Okay. So what does it mean by support structures? Support structure is referred to this. So A is actually supported by these support structures. It must supported by B and C. This is the support structure. Just now in the rockers, we just look at, is it A on the C, right? Is it B on the C? So this one, B and C will be our support structure. If correct, then we add positive. So positive what? Positive, then it depends on how many blocks that used to support the A. If 2, then it becomes positive 2. Okay. Compare to this, okay, look at this. So C supported by A and B. But if you compare to the goal, A support by nothing. There's no support block here. Okay, means that it is wrong, right? Because the goal, you don't have any support structure, but the current state is actually supported by A and B. So it's wrong, so we add negative. So what is the value here? The value is depends on how many blocks that used to support the C. You have 1 block, 2 blocks, so we negative 2. Okay, so look at A. So at this moment, A is supported by B. The support structure for A is B. So A, you have supported by B and C. Is correct or wrong? The goal state A is supported by B and C. But here, A is supported by B. Is that true? Wrong, right? So it should support by B and C. So it's wrong, we put negative. So negative, what is the value here? How many blocks that used to support A? Only 1, so negative 1. Okay, last one, B. B is support by nothing. But B support by C here. So is it true or wrong? Negative. So how many blocks that support B? 0. So negative 0, you will get 0. So you will get negative 3 here. This is the heuristic cost generated by these global heuristic functions. Okay. Alright. Good. So you have this. Let's try the efficiency of the global heuristic functions. So you have negative 3 at the beginning here. So we're using a simple hill climb first. We go to one direction. So where C put on the floor, so you get negative 1. Is negative 1 better than negative 3? Yes, definitely right. -1. Yeah, use a numbering system. 0, -1, -2, -3. 1, 2, 3. So now -1, is it better than -3? Yes, someone is like, yeah. True. You look at this, the bigger number is better, right? Because our biggest number is 3. So this is our goal. So assuming that this is our goal. Right? So -1 is closer to the 3, right? So -1 is better. So -1 is better than -3, so we can continue. We continue, we put the A on the C. So it's -1, so it's equal. So it's okay. So we go to another operation here, which is A put on the floor. We put on the floor, it becomes 0. 0 better than -1, yes. You look at this number system, 0 is closer to the 3. We continue. So you come back to -1. So it's worse than this one. So we go to other side. +1. +1 is better than 0. Continue. Now you reach the goal. Okay, so you can see that by using a global heuristic functions, you manage to get the solutions. But compared to the so-called local heuristic functions, you couldn't get the solutions. Okay, so let's move on to the next algorithms, or not next example, steepest ascent hill climb. We expand all. So same, we are using the same global heuristic functions. -1 is better than -3, right? So we expand all. So compare which one is the best. 0 is the best. Expand all. You have -1, -1, -1, +1. So +1 is better than 0. Expand. So you also manage to get the solutions. So no matter if using the steepest ascent hill climb or simple hill, you manage to get the solutions using global heuristic functions. Compared to so-called local heuristic functions, the previous case just now, we get stuck. Okay. Yes, so that is the difference between global heuristic functions and local heuristic functions. So we may take a rest for 10 minutes, right? So if you have any questions, yeah, please feel free to come down and ask. If no, then you may take a rest, washroom, or you can take your breakfast.
最高的，最高的是S 几的，SA 啊，对吧？SA 就是被抢过然后就变成我这两个差不多一样啊，一个岛最高，岛大过这个岛差别在于是两个是。看的方式不一样，这个是这样下来，没有，我再找一个出来，因为这样下来直接到手了，我直接选出来。了解，明白了。接下来，这种你打将机啊，它是 A B C 在 D E， 高顺序啊。这是 A B C D。下来这种打，这也不是
Hello, coming, faster, faster. So hi guys, we are DBA Group 5 and we are year 2 Sem 3 final year student. So we now having a civic project, and April 17, 9 to 5 p.m. we have a game booth, game carnival. If you're interested, you can follow our Instagram. And now here you go, follow our Instagram. 我觉得一个一个去比较好。If you guys don't want to scan, right, listen after me. WACOW _yourself. No one what cow yourself. 我觉得你去给他们 scan 掉。
你们有自己活动吗？Sorry?
真的咩？
都可以帮
肯定来了，肯定来了。啊，赢定
为了
了。
assignment。
Hello，谢谢你，谢谢你，不要走走的话就来玩哦。还有谁
可以帮忙
follow
follow
吗？
好好好。如果不是好哦，
肯定。
请问什么懒觉？
好哦，好好。谁要买？
那个老师要用来教的。
There are 26 different kind of game modes and we have different kind of. Others team we are not sure, but our one is like bottle ring toss game. So this ring is all 20 or 20 plus game. Different book but different price.
ringgit, so I think yeah you can take part. Huh? 6 ringgit you can play 20 games and there are a lot of prizes they say. The prize is yeah laptop, a car, condo. Oh yeah. Oh yeah yeah. Those night time I can baka one. I think it's quite fun too lah. 6 ringgit. You can play 20 games and. Oh, you attended before. It's not fun lah. Kind of. I wish to go, but a bit paiseh, no. Students still okay, still can join, but I will go a bit weird lah. People take photos and post but inside is not young. Okay, so yeah, I think it's quite good. In Taiyuan, there are a lot of activities that you can join. And I saw there's another event end of this month. The what? Huh? The music festival. There are a lot of superstars coming. Are you selling ticket? How much is the ticket? I couldn't search much information from internet, so I don't know where to get tickets. I don't know how to approach, where to approach. What's the name? I couldn't search the what, music festival. It's quite interesting lah. Okay, so welcome back. So let's move on to our next algorithms, which are the best versus and the A stars. So best versus and A stars, don't worry about this. So this actually an algorithm where you're allowed to have so-called backtracking. Okay, allow backtrack. So Silk Crank does not allow backtracking, but best versus A star allow backtracking. But there is some differences between these two. So I'm going to show you later on. So look at the best versus first. It's actually a combination of the advantage between the depth versus and also a breadth versus. So as we know that what is the limit, what is the advantage of depth versus is allowed backtracking, right? And also not without traverse all the branches. And the advantage of breadth versus is what is allowed so-called guarantee optimal solutions. So because it serves level by level. So by using this breadth versus, yes, you will definitely obtain so-called optimal solutions. Yet you do not actually trap inside the dead ends or your so-called no need to traverse every single path. Okay, so look at this algorithms. Do you want me to read out line by line? No need, huh? Okay, so I will skip this space first. Okay, so I will show you straight away, show the examples. So if you can understand the examples, you come back to these algorithms. And easy for you to understand. Okay, so this is too long, so it's not really important here. All right, so look at these examples, very important ones. You can notice that the heuristic function here is slightly different than the previous case. So the previous one is I define the number of tiles at the correct positions. So in these examples, I design another functions where the number of tiles at the wrong positions. Okay, so meaning that I'm going to calculate the tiles that at the wrong position instead of the correct position. So just now is where if the tiles at the correct position, we add 1 mark. If wrong position, we don't add marks. So in these examples, if the tiles at the wrong position, we give 1 mark. If at the correct position, we don't give any marks. It's the opposite to the previous case. Okay, so don't assume that the hungry already.
Oi.
Yeah, we don't have Muslim here. Don't worry. You have a Muslim then. Alright, so okay, yeah. So if there's a so look at this example again. So this is a goal state. That's why you get a heuristic cost is equal to 0 because none of the tiles at the so-called wrong position, all at the correct position. So all we will give 0. So add up together, so we get 0. So meanwhile here you have how many wrong tiles? 1, 2, 3, 4. That's why you have 4. So 3, 4, 5, 7, they are correct positions, so we don't add, so we just add this 4. So in this case, by using the heuristic functions, wrong positions, so the heuristic cost generated will be equal to 4. Right. So at the same time, the successor function will be sequenced up, left, right, and down. Okay, I'm not going to draw the tiles here. I will just write A. So A is referred to the state. Okay, so A is referred to the state, and then I will follow by a value 4. So it means that state A, I have a heuristic cost which is number 4. Alright, so what the goal where I want to reach is 0. Okay, I would like to reach the heuristic cost where the cost is equal to 0. So that is my initial state. Alright, so to so-called allow me to have this open and close list so that I can track which node that's already expanded, which node is not yet expanded, and which node is going to store here and there. Right. So I have the open and close list here. So to store the nodes, right? I have an A4 here. Right. So it's going to expand. So there's only one node, so I expand this A4. The moment that I expand A4, so where I can go to the up, left, right. So I have a 3 nodes, right? So I expand all, just like preferences. I expand all, I will get 3 states B, C, and D. I will get B, C, and D. So I have to use that successor function to calculate the how many wrong tiles here. So there are 1, 2, 3, 3 wrong tiles. So here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I will add this heuristic cost behind the state's name. So we have a B3, C5, D5. So then I have to add these 3 nodes inside the open list. Alright. So how to add? It depends on the value here. Okay, because your goal is to reach 0. That's why you're going to arrange the tiles, or not the tiles, arrange this state in ascending order, which is from the smallest value to the bigger value here. Because 3 is closer to 0, so we give priority to the B3 first. Okay, So what is the next? So at this moment, you have a center point here. You can move again, up, left, right, and down, right? But down you cannot, because if you move down, it's back to original state. So there are three movements here. So this is up, left, and right. So I give a state E, F, G. E, F, G. So calculate the number of wrong counts for each of these states here. 1, 2, 3, 3, and 4. 3, 3, and 4. Okay, so I expand B3. Okay, E, F, G. So E, F, G is never appears in the open list, so I can add it here. So E3 comes first because smaller. It's the smaller value. E3, F3, followed by G4. Okay, we still have two nodes here, C5 and D5. Okay, so expand E3. Expand E3. So expand E3, you can go. You can move two directions, left or right, because down you can move already. Repeated state. So you can move two directions, left or right. It's called H and I. H, I. So the heuristic call is 2 and 4. So add here, 2 comes first, H2, followed by F3. So you have the two value here, G4 and I4. So if you have the same heuristic cost, so you add according to this alphabetical orders. So G comes first, G4, I4, C5, and D5. Okay, so here is E3. So continue, which one is smallest? E2. Always start from the smallest value. E2, you give you J1. Only so-called the actions where you move this empty tiles to the down. Right, so J1. So J1, F3, G4, I4, C5, D5. Okay, so now you have these positions. You know you have to go up because your goal is 0. So now it's still 2. Okay, so J1, expand J1. If you expand this one, you can move to down and also right. You have the two movement here, either down or right. So you have two states, K, L. So K is value 0 and 2. 0 and 2. So you add K0, L2, F3, G4, I4, C5, and D5. So this is K, J and K0. If I expand K0, is it equal to go? Yes. So we stop here. So the travel path will be A, E, H, J, and K. Alright. So by using this best versus, there's no problems that you're not allowed backtrack. Yes, you can always backtrack. So in other words, you always choose the best heuristic cost that closer to the goal. Alright, so it's always check the nodes where if there's node that's always closer to the node, we expand that node first. Right. So you are clear? Okay. Can you try this question? So you have this state space using best first search. When you find where is the return path.
Okay.
Alright, so let's start. So you have opens and close. So we start with A5 first. So A5 give you B4, C4, D6, right? B, C, D. So you have a 3 notes. It's not inside the open list, so we can add it here. Alright, so continue. B, right? So continue with B. We give a priority to the first notes inside the open list. Expand B4, you get E5, F5. Okay, so we add this E5, F5 here. So, but C4 comes first, right? C4 followed by E5, F5, and D6. So B4. Right, so next, expand C4. If you expand C4, you obtain G4, H4. Okay, so G4, H4, E5, F5, D6. Okay, followed by G4. So G4 give you F5, but F5 is already here, right? So we don't ever add it. You want to add also can, okay, but we don't add. So if you add also, not add also, doesn't matter. Eventually we will still go to this path, right? Later on you can try another example where you put another E5 somewhere around here, okay. So continue. So which is H4. If you continue H4. If you continue H4, you will K2. Okay, K2 comes first. K2, E5, F5, D6. So continue K2. Okay, K2, no solutions. Okay, if no solution is okay, we continue to E5. We continue to E5, E5, no solutions, that end. F5. So F5 give you J0. Right, so J0, D6. So continue J0. So this is the goal. So that is your search path. So your return path will be A, B, F, J. That's it. Okay. So what I'm doing here is actually how the agents, how the algorithms actually perform. The agents will perform the search, then eventually reach the goal, and then this is what we will see on the screen, and this is actually searched by the agent. The agent is the computer, the agent is the computer. Okay, you mean like you want to add the F4, is it? Okay, let's say you add the F4, okay. So, where is multiple? You can actually go to F5 also, right? So, here F5 you can actually select. It's actually from D.
考虑看到
So, but eventually you will still expand this one first, right? Do you mean that this one also can go to F5? The value for
因为你就不做什么，
right, that's all. I give for example. Oh, okay, it's not okay.
我跟老师对用。 做的嘛，自己做的，就是这可以，你们可以做这个可以打勾这边就发，就是可能是。
Alright, so that is the best versus. Let's go to the last algorithm, which is A star. Okay, so what is the difference between breakfast and also A star? So all the while we learned hue crimes and we learned the baskets. So these two algorithms depends on only one parameter, which is heuristic cost, right? Using the hue crime, use the heuristic function, generate heuristic cost. First, just now in this case, we also generate heuristic cost. But what is A star? A star is actually quite similar to one of the famous search called Digistra, where have been commonly used in more of the search engines like the Google ways they're using this search. So A star using a two parameter instead of heuristics, we call it as function cost. So function cost is Hn plus Gn. Okay, so that is the only difference. So hue crime baskets use Hn, but A star use Hn and Gn. Inside the questions, you are given these two parameters, Hn, Gn, then you definitely have to use A star search. So what is Gn? Gn is the total distance from the current state from the so-called initial state. Let's say you have an A here, you have a B here, you have a C here. So A travel B is, let's say, 5. B travel C is equal to 4. Alright, so what is the function cost for C, let's say? So this is equal to the total so-called step cost from the initial state, which is 5 plus 4. Plus the Hn. Okay, Hn normally will be given, let's say the Hn for C is equal to 10. Then the Fn for this case will be 19. Okay, Hn will be given, it could be Euclidean distance, it could be Manhattan distance, and other heuristic functions that you have seen earlier. Calculate long tail, calculate correct tail, they are all heuristic functions. It's what you have learned just now. Something new is this Gn. Okay, what is Gn? It's the total cost of the current state from the initial state. It's Gn. You just need to add these two parameters, give you Fn. Alright. So what is Euclidean distance? You will still remember it's actually x1 minus x2 square plus y1 minus y2 square right? But you don't really need to know this. Normally question will be straight, it will give you the value. Manhattan distance will be another way to measure the distance between 2 points. It's be 1, 2 minus plus y1 minus y2. Okay, don't worry about this equation, it's not very important. Just to let you know that we have a different type of heuristic function that used to generate this heuristic cost. Okay, so I'll give you one simple example of how to calculate the Manhattan distance for the so-called sliding tiles. So assuming that you have this goal state, so you have a 1, 2, 3. So you have a current state. So the current state is like 1, 2, 3. Alright. So how to calculate the Manhattan distance for this current state? You just need to compare tile by tiles. Let's say the first one, 2. So how many slides that you have to move so that this number 2 here will immediately reach to the goal state? How many slides? You just need to move to the right hand side, right? You need to move to the right hand side, then you reach the goal. So we are going to assign positive 1 to this tiles. Value 3. So how many tiles or how many slides you got to move so that you can move immediately from 3 to the goal state? 1, 2. So assign 2. 1. Okay, how to move to this goal state? 1, 2, right? Or 1, 2. So same, so 2. So 2 plus 2 plus 1 is equal to 5. So the Manhattan distance for this case is equal to 5. So this is one of the way that you can measure the heuristic cost. Okay. Alright. Okay, so that's not very important because we're not going to use that. We're not going to use this for the next examples here. Alright, so this is the real case studies where we are going to measure or we are going to find the shortest path that can travel from this position Ara to the Bucharest. So that's actually a state space. So the value stated here is actually the distance, or you can assume that this is the stack cost. So this is the position Ara, Gerins, Arade. So this is the position, and the value here is stack cost. So the value here, straight line distance to Bucharest, is actually referred to Euclidean distance, which is referred to Hn, the heuristic cost. Alright, so you have the heuristic cost, you have the stack cost, which is these two parameters, then this is A star questions. Okay, so you can use these two parameters, Gn and Hn, to find you the shortest distance. Alright, so how to start? Right, so that is the initial state, right? There are many paths, right? You can travel from here to go to the goal. You can travel to here to the goal. You can travel from here, go. You can travel to here to the goal. Which one is the shortest path? Then we are going to use this A star to help you. So always remember, A star is consists of the two parameters, Hn and Gn. So let's start step by step. Alright. As usual, I'm going to open these two list, open and the close. Okay, start with the Arat. So Arat, what is the Gn and what is the Hn? Because we are going to find the function cost. What is the Gn for Arat? Initial state Arat, and then your so-called current state also Arat. So do you have any step cost? No, so it's 0. What is the Hn for Arat? Look at this. Arat is 366. So the function cost is equal to 366. I'm going to add this A366 here. So now I expand A366. So I expand Arat, I can travel to 3 different places: Zarin, Sibiu, and Timisoara, right? So I can travel to 3 places: Sibiu, T, and Z. I have a short formula. I just denote as S, T, and Z. So what is the Gn and Hn? So you have to measure the distance from A to S. What is the distance? A to S, 140. Right. So 140 plus the Hn. So you have to find the Hn for CPU. So you have to look from this table, CPU, where is CPU? 253 plus 253. So what is the total? 393 right now. Okay, how about T? So what is the distance from A to T? Look at this map. A to T, 118. So which is 118 plus 329. Okay, how many? 4, 4, 7. Okay, the last one, Jack. So what is the distance to Zarin? 75. So 75 plus the Hn, 374. So you will get 449. So that's it. So you can travel 3 different places. So again, arrange them in ascending orders, right? So if you have 3, 9, which one is the smallest? So this one. So S 393 followed by T 447 followed by Z 449. Okay, so we expand the one with the shortest distance or shortest function cost 393. Expand CPU 393. So expand CPU where you can travel? You can travel 4 places. Already back to Arad, Faragas. The last one is Visia. Remisia, Visia. So you have 4 places here. So you can actually travel to 4 places. 1, 2, 3, 4. Okay, but however, you actually travel from Arad, so you probably don't want to go back here because repeated state. So Arad we give up. Okay, so there are 3 more places: Faragas, Aradi, and Visia what? RB. RB. So again, you have to calculate the function cost for these 3 places. So I'm not going to show you the GN and FM. So I just show you the value here: 415, 671, and 413. All right. So you have 3 replace. So you have to add these 3 into the open list also according in ascending order. So F first, because 415 is smaller than 447. Sorry, supposed to be 413. 413 followed by 415 followed by 447 followed by 449 and last one 671. Okay, continue to expand RB. Okay, expand this RB here. You can travel Cebu, Crabola, and also Vesti. So we have 3 different places. Okay, so I'm not going to calculate the GN and so-called the HN. So I will just write the value here: 526, 417. Okay, and then Cebu you have already traveled here from before, so we are not going to have a repeated state, right? So you have 2 values here, so adding inside here, so you have F 415 followed by P 417, T 447, Z 449, followed by C 526, 0761. Okay, continue Paragraphs. Okay, Paragraphs is the list number now. Expand F415. If you expand F415, you can travel 2 different places: Cebu and also Bucharest. But Cebu is already traveled before, so we don't expand. So B here you have 450. Okay, so again add in. So you have a P417, T447, Z449, followed by B450, C, and 0671. Okay, although the successor is the goal, Bucharest, right? But however, we didn't expand, right? We have to always check the close list. right? So this is not the goal yet, so we expand P. Okay, we expand P417. If we expand P417, so which is capacity here, it will give you 3 different places. Okay, which is B and C and RV. Because RV expand before, so we don't travel again, repeated state. So we have 418 and C is 615. So add inside here B418, T447, Z449, and so forth. Alright, and finally expand B. So this is our goal. So this is the goal. So we stop here. So the travel path will be from Arad to Sibiu, Sibiu to Visya, Visya to Presti, and also Puchara. So that is our return path. Yes. Okay. So it depends on 2 parameters, remember. It depends on the GN and HN. So meanwhile, for the best versus, it only depends on the heuristic cost. Okay, so normally this so-called the best first will be applied into the map lah. It's more suitable to apply into the map because we need to obtain the Euclidean distance or a Manhattan distance. So I know it's a little bit of kind of complicated to understand, but the difference of the orient is very obvious. Alright, so I'll give you a summary of the search, the orient that so far we have learned. Alright, so there are 2 types of orients here, blind search or heuristic. Okay, so this is uninformed. So this is informed. So blind search mainly from breadth first search and depth first search. So both are pattern based. Okay, so this is horizontally. So this is vertically. So heuristic, we learn about hue crime. Okay, so hue crimes, there are 2, which is simple hue crime and steepest ascent hue crime. So steepest ascent, simple hue crime is like depth versus one direction. If no, we go. Okay, but always remember, no backtracking. Okay, steepest ascent is expand off. Okay, expand off. So, and then we have a best versus. Okay, so best first, allow backtracking. And then last one is the A star. So we use Fn instead of Hn. So this one we use Hn. This one also. That's the summary. Okay, so although the examples look very complicated, yeah, and then maybe you still cannot spot the difference. But always go back to the theory, yeah. Then you go back to the so-called example. Then you can spot the difference. Okay, so probably you can try these final questions here. Okay, you have this state space. So this is the station, SAB stations, and the value here is stated as the stack cost. So you have a stack cost, you can find the GN. At the same time, you have a table 1 indicate heuristic cost, HN. So you have a GN, you have a HN, you can use A star search. Alright. So yeah, I'll leave it to you, these questions. You can try. And yeah, I will show an answer later on. So let's try together. So I give you 5 minutes.
Friday okay online lah, but 现在typical all first lah, most of the lectures are very good because we need to prepare the final things, send this to later, check. But yeah, we have an example for that, but I don't forget that's the yeah, normally the industry one is just one it's not industrial, right? And they're not speaking because just my experience some really is very but some of them is like they just go like they already started at this if I haven't started to collect the data so I have to wait sometimes I don't know once collect the data so it's better when we do our own thing first and then okay do not the tool itself maybe we can integrate lah
我都买Audi了，我都买Audi了，Audi的可以拍除非在家吧。
Okay, I think this is the test 3, right? As explained to A and B, you get a function called gn plus h 18, 17. So we always choose the smallest one. This is 17, continue. So B can only go to donkey, right? If based on the state space. So again, what is the stack cost? You have to calculate from S to B, B to D. Yeah? This is S to B, B to D, and this is the HN, 16. 16 is still better than 18 among all, right? So you compare all. So 16 is still the best. So D you can actually compare to expand to A and G. Why I have an A here, although there's an A, because A no yet expand, so I still can go to A. So if you still remember to the previous case, I have a Bucharest here. I can also have another Bucharest here. So as long as no yet expand, we still can put inside our open list. Right, so we go to A and G, so calculate the Fn is 29, so this is 10. So 10 is best among the all, so we expand G and compare if G is equal to go. Yes, it's equal to go, then we stop here. So that is our return path. Yeah, I don't, that's all for today's. Yes, so we managed to make it before 12. I know there's a lot of information for these chapters. Yeah, it's not considered as calculation. It's not calculation at all. It's just different algorithms, right? So you have to not really need to memorize, but the more the exercise you do, then you actually will automatically remember, right? The way it expands. So yeah. I have already provided you the quite number of examples, and you have some examples also in the tutorials. So try not to miss the tutorial as well, and do revisions before midterm and also final examination. So this topic is very important.